So now that we have an understanding of the formula for the scalar product, let's talk about actual applications or use cases here. So I want to talk about two very specific ones that usually are applied in engineering. So the first one would be to find the angle between two position vectors. So find angle two position vectors. And how do I do this? So for that, I just need to use the two formulas that were just given to you, right? And so I repeat them. A dot B is nothing else than A magnitude, B magnitude, cosine of theta. But it is also equal, remember this, it's also equal to AX BX plus AY BY plus AZ BZ. So I can set them equal and really solve for this angle, right? So all I have to do is bring these over to the other side so that the cosine of theta, so cosine of theta is really equal to AX BX plus AY BY plus AZ BZ. And the whole thing divided by A magnitude and B magnitude. And remember that the magnitude of a vector, or even in 3D, is just the Pythagorean theorem, right? So I have AX squared plus AY squared plus AZ squared, and then square rooted. And remember, this is then multiplied by the B magnitude, which is BX squared plus BY squared plus BZ squared. And that also is just square rooted, so that the formula now applies, and now I can find the angle between two vectors. That is something very useful for engineers. If you have two position vectors given, now you can find the angle between them. And I believe that we don't have to really exemplify this or elaborate on this. I believe this is very doable. However, what's often new to beginning engineering students is the second part, which is to use the dot product or the scalar product to project one vector onto another, or I should say to really find a component, a parallel component. So to find parallel force components. And the way that works is you use the scalar product, so use scalar product to project, and project is a word that I use, one vector onto another. But the another vector needs to be technically a unit vector, right? So it needs to be unit vector. And you will see in a second what I mean by that, but please understand that this is important for now. Because if you do not project the first vector, let's say A onto B, and you do not use the unit vector for B, then you actually multiply the magnitude by vector B. I guess it's better if I write that down. So let's say you have A dot B, and you're looking at two vectors. Let's make a small drawing of that. So let's say you have A here and B there. So A vector and B vector, and of course we know that in between we have the angle theta. And remember that I write it once again, a dot b, so that we won't forget this, cosine theta, right? That's really the definition of the dot product. And really what this does, right, is you take the cosine of a and theta, if you will. So what do I mean by this? Let's say I know the magnitude of a, which is the length from here to here, and then I multiply that by cosine. Let's forget about the b for a second here, but let's say I multiply this by the cosine of theta. What do I really get? This part here, right? So let's say there's a 90-degree angle here. This component here, this is really a magnitude times the cosine of theta. So the b is actually a multiplier in this case. So you can think of b as intensifying this component. So what engineers like to use the scalar product for is to find parallel force components, or like parallel components, if you will. So how much of A is parallel in B, if you will. And that's why I call it projection, the dot product, because you really project this force onto this baseline here. And one way to make that happen is, instead of using B, you actually use the unit vector of B. So what would that be, the unit vector of B? So you remember that a unit vector is always a vector that is parallel but has a length of 1. So let's call this vector B hat. So how do I get B hat? B hat is nothing else than B components, or the vector, divided by B magnitude. So that ultimately, if I want to find a parallel component, so to find parallel component, to find the parallel component, all you have to do is to say that A magnitude times cosine theta is multiplied by B divided by B magnitude. So that would really give you the parallel force component. And that is something that initially seems a little bit overwhelming, but a short problem for that will be shown to you in just a little bit so that you can practice that. Before we do that, let's show one more case or one more application here, which is very similar to this. And for that, let me draw, or let's actually write down 3, which is finding force components along x, y, z axis. So for that, I think a picture is better than anything else. So let's draw a 3-dimensional coordinate system. Let's do that right here. So I have a 3-dimensional coordinate system. And usually we have x, y, and z. And let's place a force in it. So let's say the force is acting in this direction. And we, of course, understand already the directional cosines and things like that. But for visual representation, I need those lines anyways. But let me just show you that, for example, here I have the angle beta. Remember that? That's between the vector and the axis. And now if I include my base vector, which on the y-axis would be nothing else than j hat. And so now you can imagine that if I have, let's say, a vector here, and let's call that f vector, so I can find fx, right, fx, by dotting it onto I. So by fx is nothing else than f vector dot onto I hat. And that will give you actually the value of the x component of that particular force. Why is that? Because you would just have something that is F magnitude times 1, right? Because that's the unit vector, times the cosine, in this case, of, well, actually, in this case, it would be alpha, because I'm talking about fx here, right? So here I set fx, and here I use beta, so let me fix that, or let me write that as well. So fy would be equal to f dot j, which then would be equal to f magnitude times 1 times the cosine of beta. And for the last angle here, gamma, it would be the same concept. So you can always use the scalar product to find certain components. So let's talk actually about case 2 and case 3 here, because those are very identical to each other or very similar to each other. You always find the projection onto an axis or onto another vector. And this is visualized here for 2D, but it works wonderfully in 3D as well, as you will see in an example in a second. But to complete this, there's not just, of course, a parallel component, there's also a perpendicular component, and similar to this concept here. So let me actually draw the missing line in here that we, of course, remember from our last lecture. So that the angle there is actually in a plane that is spanned, like here is the end of the plane, and then we have technically a right angle down here. So that means that this here would be the part that is perpendicular to the y-axis in this case, right? So that's similar to what's going on here. This part is perpendicular to this part. So how do you get this? You can, of course, use other mathematical vector operations, but that's not the point of today's lecture. The point here is to actually recognize that we're looking at a right triangle where the hypotenuse in this case is A, right? So this is the adjacent and this is the opposite. So you can, of course, use the sine then for this side, if you will, but you can also use Pythagorean to take this side squared minus this side squared. So for example, let's give that actually a name here. Let's say this is h, the height, and so h squared plus, and now I'm going to use what I wrote there, a cosine theta, and that squared is equal to a squared, right? That's what that means. And then down here, where you have the perpendicular component, you can also say that perpendicular component squared is equal to f squared minus the component that we wrote down here. So minus, let's see, f magnitude times 1 times the cosine of beta, and that also squared. So in other words, this is all Pythagorean, what I've just done here. So this is Pythagorean, this is how you know it, a squared plus b squared c squared, if you will. And here I solved it like so. Here's my hypotenuse, and here's a component, here's a component. Whereas the hypotenuse in this part here is up here. But that, I think, completes how you can look at these scalar products and how do they relate to each other. And I believe now we are ready for an application and a problem statement.